Good morning, everyone. Very welcome to our webinar series. We can wait a couple of more minutes, maybe just to make sure that all presenters are here. Yes, I just double checked. Everyone is here. Then we can start right away. I see that we have more than 20 participants. Lovely. Yeah, again, very welcome. Today's webinar is called Robust Perception of Autonomous Vehicles. My name is Eren Aksoy. I'm an associate professor at Halmstad University in Sweden. And I would like to just inform you that this webinar is organized under the shelter of Horizon Europe project called ROADVIEW, which stands for Robust Automated Driving in Extreme Weather. I will give you more information on that very soon. So, and the subject fits very well to our research program here in the project. So we are happy to organize the third edition now. Before we start, I would like to share a couple of housekeeping rules. Be aware that this event is going to be recorded, and it will be also shared with public on our webpage and social media channels. So if you do not want to be part of that, please inform us through this email that we have on this slide. And Julia is actually the person who is going to take care of all these organizational issues, and she's also here, one of the attendants, so you can drop a line there. Very important note is that we have two boxes in the webinar. On the top left, you can see one is for chat, which is basically dedicated to notify us if there is any kind of technical issues that you are facing, but no questions, please, there in the chat box. So we have a dedicated box, a Q&A box, where you pose your scientific questions. So if you have anything, please post it there, and then we will take the questions basically after each talk. But we're gonna have also panel discussion right after all talks. So the idea is that we will collect all those questions through the webinar and then address them in the Q&A session, which is going to be at the end of the talks, 3 talks that we have today. So maybe I can tell you a bit about like what is this ROADVIEW webinar series about. So we are having a series of webinars on CCAM activities featuring participation of global experts in the field. So we have invited different stakeholders, companies, research institutes or academic institutes. We are planning to have like one webinar in every 6 months. And the main scope is to raise the awareness about the CCAM solutions, because there are huge participants in this CCAM activities. So we would like to share experiences and ideas. And we would like to also present CCAM technical challenges that we are facing. There are a bunch of it. No worries, there are a bunch of to share. And also we'd like to introduce ROADVIEW innovations. So in this project, we come up with a bunch of more than 10 innovations that are highly relevant to CCAM activities. So we'd like to share our experiences with the others. Of course, we'd like to share raise awareness about the CCAM partnerships so that we get more active participants. And we would like to advise on standardization and regularization requirements, because again, recalling the fact that ROADVIEW is just about extreme weather conditions. I mean, autonomous driving in bad weather conditions. There are many things that have not been addressed before. So we'd like to feedback the standardization and regularization bodies to consider those feedback, especially when it comes to bad weather conditions. And also, the last but not least, we would like to present the market applications of the ROADVIEW technologies so that the OEMs and tier 1 companies are aware of all those solutions. So it's a 4-year project, and we are more than halfway done, and there are still many there's still time to go. So if you would like to learn more about our activities and the project results, I would kindly ask you to get subscribed to our newsletter and event reminder, which will be shared. The link will be shared soon in the chat by Julia. And you can simply follow our LinkedIn post as well. All right, so this is the third webinar, and it is dedicated to robust perception of autonomous vehicles. And here you can see the schedule for today's session. And we start with myself, like I just give the welcoming words and these introductory slides. And then we are gonna start with our first speaker from Valeo, Sergio Fernandez. He's gonna be talking about reaching robustness against environmental artifacts in dense point cloud, which is highly relevant to AVs. Most of the AVs are nowadays using point clouds, either sparse or denser, but I'm pretty sure he will gonna share his experiences with us. Then we are gonna have this next speaker is gonna be Jyri Maanpää from FGI Finland. He's going to be talking about optical measurement of road grip and road surface conditions in front of the vehicle. So it's a very interesting study conducted in ROADVIEW, which is showing how we can estimate the slipperiness of road surface by using sensor fusion or fusion of different modalities, not only camera and LiDAR, but there is also interesting sensor that you should be, I think, seeing. The last speaker is Petri Manninen from FGI as well, Finland. He will be talking about environment-aware high-definition mapping method for real-time positioning of an autonomous vehicle on the map. So it's also about creating a map and localization of the vehicles by using semantics-aware information. It's also conducted in under the ROADVIEW project. Once we have all those talks, we will be then having the Q&A session where we'll pose your questions to the speakers. Maybe I can say a couple of words about each speaker. The first speaker is Dr. Sergio Fernandez. He's a senior expert in LiDAR, working at Valeo in Germany. He is actually a technical leader in computer vision algorithms at Valeo in Germany. And he had also internship researcher in Glasgow University in the UK. And he's holding a PhD in computer vision from University of Girona in Spain. He is an expert in the fields of computer vision and AI, particularly in applications in autonomous vehicles. Next speaker is Jyri Maanpää from Finnish Geospatial Research Institute, FGI. He's a research scientist at FGI. He is actually conducting his PhD at Aalto University in the very same city in Finland. He's holding a Master of Science and Technology from Aalto University. And he's an expert in deep learning, computer vision, and autonomous driving in adverse weather conditions. The last speaker is Petri Manninen. He is also from FGI Finland, and he's a senior researcher there. He is also a PhD student at Aalto University in Finland, and he is holding a master's degree in robotics and autonomous systems. His expertise is in the mobile laser scanner, LiDAR perception, LiDAR odometry, and HD map positioning. Right, that's all from my side, and and here you can see the whole list of the ROADVIEW partners, consortium members. We have like 15 different partners. No need to name them one by one, but you can see the list. Okay, with that, I will stop now sharing, and we will start with the very first speaker. Let me welcome Sergio Fernandez. Sergio, if you're there, maybe you can turn on your camera first and start sharing your screen. We can see your slides. Very good.
Is visible?
Visible.
Okay, perfect. Thanks, Eren. And thank you for the introduction. So let me start right away. Topic I want to present is reaching robustness against environmental artifacts in dense point cloud. Let me guide you through the points to highlight here. First is to understand the need. So to understand what are the constraints on level 3 and beyond that we need to fulfill already at the present. And then what are the constraints not only from the outside, but also from the inside regarding the data. So what has been the evolution of LiDAR data and LiDAR technology in the past years? This will give you an overview what are the challenges and mainly what are the problems or difficulties we face in LiDAR technology, specifically for robustness capabilities. So what are our tools to fight against environmental effects, other kind of effects that all of them together affect the point cloud and might affect the capability to reach level 3 and beyond. Then I will first present some model-based methods, so geometrical methods, and we'll then move to AI methodologies. So to compare what has been done till now and what is being done from present to future. I will then shortly mention in relation to the AI methods, what we use for automation, because that's crucial to have a good database to train the network correctly. And then come up with some complementary topic on H3 radar and reach the conclusions of all the points together. So first starting, what is our ecosystem? What is we need to reach level 3 and beyond that? Yes, summarize here in slide for level 3, what are the challenges we have already achieved? So automated driving up to 60 kph since January 2021. That was the project we worked together with Mercedes. And now since last year, it has been extended to 130 kph. So this is now autonomous on level 3. It is on 2 customers that we have participated. One is Honda, the first, and then Mercedes in Europe. So I think the one from Mercedes, the one you might recognize with some advertisement last year, that they are now reaching the level 3 in highways. And this thanks to our LiDAR and to our perception capabilities, because we sell not only the sensor, we sell our perception on top of it. Then what is the next milestone, the future, to reach level 4? There is a working group ongoing, and the goal is to have fully automatic driving in predefined areas, and this is going to be achieved on predefined areas, probably by robotaxis first, but also on normal autonomous cars in the near future. So this level 4 is not only greedy in terms of regulation, it's also greedy in terms of ODDs, scenarios we would need to cover. If we are talking about level 2, where we started with, we were covering the main scenarios to reach, let's say, 98, 97, 99% performance, but some scenarios were not covered. Does not matter. It was not on the ODD. Now, when we go to level 3 and before, beyond going to level 4, we need to also cover those that can appear very sporadically, but can be really critical for autonomous driving. And this is the challenge. This was what is, you know, the long tail in the training, because we will never have so much amount of data to train those scenarios, but we still need to perform whenever it happens. So from the constraints on the road type to debris on the road to vulnerable users of the road to also, let's say, so not normal or non average cars, trucks, like any odd-shaped vehicle or any vehicle carrying some, some overhanging load, or something that is not in the normal database or might not be in the normal database, and we need to cope with that. And why I'm relating the perception with robustness? Because we cannot simply train our model saying those are the normal types of cars and the rest is filtered out and assumed it is noise. Yeah, we need to be able to distinguish what is real noise and what is actually happening on obstacles, on targets, and we need therefore to detect. That's from the outside requirement. Now coming to the inside requirement, what has been the evolution on the LiDAR data itself in the past years that put us an extra challenge for the robustness and for the perception? This has been mainly the payload. So we've been coming, and I'm showing here two Valeo LiDAR sensors, the previous generation Scala 2 on the left, and the current Scala 3. And we are working already on the next generation with even more data. This is more than 1 million points in the scene in one frame and at a rate of so 1 million, more than 1 million points per second, and a rate of up to 20 frames per second. So it generates a huge payload to process. And on top of that, not only the raw data itself, if the customer asks to provide perception capabilities on top, then we need to add it on the raw data, on the data, sorry, we send to the customer. So this put us in a compromise. We need to process huge amount of data. We need to process it and cover many different ODDs, and we need to have it in real time. Up to some customers require up to 20 frames per second. So this is not an offline processing, and therefore put us on the challenge how to cope with this in real time on top of an embedded software. Yeah. So now you have an idea already of all our constraints. Now let me show you what affect LiDAR data the most, and those are two effects, mainly environmental conditions, road conditions, and I would say also a third that are sensor artifacts. So regarding environmental conditions, snow, fog, spray, they play a bigger role. They can create a very dense point cloud, actually as dense and as energetic as a real object. But we need to be able checking the point and the cloud together and distinguish those from real targets. Here it's some example of the effects of those environmental artifacts on the Scala 2 data. Now let me show you what it looks like in Scala 3 data. This is a heavy raining scenario on the highway, German highway, and we see those effects here, spray below our leading vehicle, creating a huge dense cloud that it is impacting not only the detection here, but also beyond. So it is hindering that we are reaching visibility beyond that cloud. So this is example coloring by distance, so coloring by layer. You might know that the LiDAR provides up to, in our Scala 3, 520 layers vertical. So it is affecting most of the layers focused on the obstacle detection. So it really creates a problem of visibility. If we distinguish by echoes, let me explain you that our LiDAR provides several echoes in a single shot, in a single ray. We are able to gather different reflectances. That is exactly for this reason, because in the case there is rain or there is fog or spray, our laser might be able to go beyond that raindrop, target the real obstacle, and come back. All this information can be retrieved and can be sorted in different time spans. And each of those time spans represents an echo here in a 3D point cloud. And that is helping us to say, okay, which of those reflections are at which distance. So we might even be able to distinguish at a first shot that if there is one echo and beyond that there is another echo, probably the first one is not true, or probably the first one is, let's say, something to look further. It might be that it's actually a real object that is semi-transparent, or that the ray is hitting only partially the real object, but it's in any case something that we shall look for in the algorithms to filter. If we are dealing only about one echo and all echoes are smoothly in place in similar radial distance, then we are probably not dealing not dealing with a spray or with a range scenario, but with a normal obstacle. Here, I want to show you how we categorize the impact in our expectation for customer to say, okay, we are talking about rain, but this can be categorized in no rain, light rain, medium rain, or heavy rain, and the same for snowfall, spray, and fog, because we will therefore be able to provide different performances, different KPIs for each of those 4 levels. It is important when we talk with the customer what can be reached, that in different environmental conditions, that we categorize numerically which levels of those impacts are we dealing with, and which KPIs will be applied for each. It is not the same, therefore, to have so we will not have the same KPIs for different levels of rain, snow, and so on. The values are quite standardized, so I think it's good to have a look at to understand that only in no snowfall, no or light snowfall, we will probably still be having the same KPIs as in good weather conditions. But as soon as we increase the effects, probably the KPIs will drop. And how will they drop? They can drop in 2 means. They can drop in range detection, but they also can drop in the TPFN rate, because we might be losing detections, we might be tracking badly. If we are talking about the high-level tracking, we might be losing the object due to some occlusions caused by rain, dirt, or so on. So this also impacts in the end the KPI. About the range itself, where we are able to reach, this is more estimated on the first meters of the receipt point cloud. In the sense, we have some algorithms that detect if there is a lot of disturbance at the beginning of the point cloud, then probably we will not be able to reach the full KPIs at a far distance. So those algorithms are called blockage detection algorithm and range estimation algorithm. So they are provided together on runtime with the high-level perception, so that the customer knows, hey, I'm getting lane detection or object detection, but the range signal is indicating that it is low. Yeah, so I probably shall not trust what is happening in a far range. Here, comparison of what we are able to provide before with Scala 2, but now mainly with Scala 3. So precipitation, different levels of, as I said, some granular levels, what can be detected also for aerosol and for spray. Let me not spend much time on that. And now, said this, let me go directly to what we use currently, AI-based model for filtering of effects. This is only an example. This would be the ideal world: no rain, no effects in the scenario, and probably with a very, very basic AI model, we are already able to detect what is an obstacle and what is not. But that's not the real life. On the real life, let me go back, we will be impacted by all those artifacts you saw. And for that, we need to create a more clever detection. On top of it, We need to fit on the chip and run in real time. That's why we cannot just take a super powerful network and play it all offline. We need to see what is suitable on the SOC. In our case, this is an example of one of the networks that fits for us. This was on the context of some master work to analyze which networks could be fitted the best in an embedded SOC. So this is an example. A unit can be really suitable for our purpose to distinguish obstacle and to discard environmental effects. We tested among different options and turned out unit and deep cellular unit both perform quite well for that. I will talk later about the left side, about the auto annotation, but now focusing on the network itself. That's the basic architecture of it. And then let me show you that our goals were not only to reach the best accuracy, but also to fit on the runtime. So as you see here, even if the noise detection was at relatively high level, some models were not, and that's why you see it does not really look clean. We then tried residual unit. We saw improved performance for some of the classes here, but when we come to the overall values, they were still not so convincing. And for that, we thought, okay, let's apply generative AI to better train the network. We might have not enough data of some scenarios, so let's increase that using some GAN models so that the network can distinguish better what is obstacle, what is not. Here I already discarded noise performance and focus only on obstacle. And on the top, you see the performance of the unit I just showed. On the bottom, you see the performance applying GAN with unit. So you see there is an improvement in all the classes. So we can expect that, yeah, it is not the ground truth, but if then we would apply some clustering and filtering, probably the object detection itself might be sufficient. And then came the point to fit that network on the SOC. So to reach the latency that we are required, those 20 FPS, we need to do some quantization. And quantization comes often with a drop in performance. So we were comparing which of the networks perform better for it. And we saw the normal unit with 16-bit quantization can be taken at the best because we are still below the, this will be for sorry, this is a typo, this is milliseconds, this will be then 20 FPS. And then, no, sorry, 47 FPS, so we are on the 20 FPS and still the performance is 94%. So we came up with the conclusion, training a unit with a GAN architecture and then quantized it to 16-bit performed for us on the selected SOC the best among all the options we had. And that is for the approach we are trying to implement now very shortly about how we take the data, how we do the auto annotation. We cannot rely on manual annotation because this is not costly effective and not probably even qualitative effective. So we are trying different auto annotation models. The good thing is that we can use some image-based models like YOLO and apply it to the LiDAR data. We just need to project it. And this is what we are using. So selecting, depending on the classes we are interested on, different models which perform better. For example, guardrails. So we are using GSM-based grounding Dino. For normal cars, YOLO would be the best. So we are selecting, depending on the class, which model to take the data from. And this is our auto-annotated labels that we use for the training. some examples here. Yeah, then let me come to before conclusion to the last slide showing in general, LiDAR has problems with environmental models and might have range detection issues. On the other hand, Valeo also working with HC radar, which appears to be better to handle adverse weather conditions, so less prone to errors due to that. So one idea would be from the customer level to apply both outputs in a fusion model, or even to on the low level fusion to fuse the data directly to discard the artifacts of the LiDAR. So this is some ideas we are working on, and I think if the customer is convinced they need the two of the devices, then probably low level and high level fusion would together help to reach the robustness. So let me now come to the conclusions. Level 3 application requires managing of different environmental effects. Latency is the biggest constraint to run AI-based models because of the constraint on which networks have which runtime, and also which layers are supported by the SOC. Model-based algorithms can help and can be therefore combined or even used as part of the training. And if nothing of that helps, there is always the idea to combine different sensors with like LiDAR, edge radar for the fusion and the perception. So as a summary, we see the future in hybrid models, means geometrical and AI combined together. In many matters it can happen, but there are in any case benefits of using that, and this is what we are working on now. And with this, I finish presentation. So thank you.
Thank you very much, Sergio. It was very interesting. It was fun to listen to you. I really enjoyed your talk. Thank you very much. Just a side note, if you have any questions, please post in the Q&A part, and we'll then get back to Sergio once we are done with the remaining talks. Thanks a lot, Sergio, again. We'll get back to you soon. And now the next speaker is Jyri. Jyri, if you can, I hope you will not face the same technical problems.
Hello,
maybe
do you hear
exactly,
me?
We can hear you. Thank you. If you
Yes, that's
simply
great.
share your slides, I will.
Yes, can you see this?
Yes, finally. Thanks a lot. And stage is
Okay,
yours.
that's great. Yes, so hi everyone. My name is Jyri Maanpää, and as introduced, I'm a researcher from the Finnish Geospatial Research Institute, FGI. I'm talking about this slipperiness prediction related to this ROADVIEW project with this title, Optical Measurement of Road Script and Road Surface Conditions in Front of the Vehicle. So, as you probably might know, in this ROADVIEW project, we are kind of like solving how to do autonomous driving in challenging weather conditions, for example, snowfall, which is quite common here in Finland. Maybe not now, but quite usually. And then there might be low visibility because there's snow in the air, and of course the snow accumulates on the road and makes it slippery. Of course, rain can also make the road slippery, but still people, they have kind of like, they have some kind of like intuition how to drive in these slippery conditions. They know that they should follow these road tracks while they're driving because they are less slippery than the snowy areas on the road. And therefore we think that autonomous cars, they should be able to do the same. But actually, as autonomous cars, they have sensors that kind of like are beyond human sensing, kind of like beyond human senses, because they can sense things that humans can't see with their eyes. So maybe those ADAS sensors could be actually even more accurate in showing how slippery the road is. So these are the challenges that we are solving in this project. But first I want to get us on the same page. What is the grip as a phenomenon? So here I have a picture of a car tire on the road, and the tire is rotating this way as the car is going forward. And the car has weight, and therefore it has gravity G, and the road supports the car tire with an opposing supportive force N. As the driver presses the throttle pedal, the tire pushes the road back, and then the road starts to push the tire forward with this friction force F mu. And the thing is that different surfaces stick together within different amounts, and there is a limit when how well the tire stays on the road, and and at some point it starts sliding, and it depends on this supportive force and this static friction constant mu0. And this is what we want to know on the road, that when does the car tire start sliding, and we want to avoid that to maintain the control of the car. And it depends on the surfaces, so basically asphalt and tire, they stick quite well together, and the grip is around 0.82. But then snow and ice, they have smaller static friction constants. So that's the thing that we should know if the road is slippery, if it has snow or ice. So that's what we are trying to investigate. Here's our research vehicle, Arvo, and it has quite a lot of different sensors, and we have collected quite a lot of data with it. But first, I want to focus on how we actually get the reference for those grip predictions. And in that, we use this road weather sensor, which is in front of the car here. So it's a optical road weather sensor. The model is Vaisala mobile detector MD30, and it uses infrared spectroscopy to measure the grip on the road. It has 3 infrared lasers that it is pointed to the road, and then some of the lights gets back, and then the sensor measures the intensities, kind of like how much of the light from each of these 3 different wavelengths return to the sensor. Then, based on the physics of water and ice, we know that different wavelengths are absorbed differently from water and ice, and then for the sensor has a formula, and then it kind of like somehow decides what is the water and ice layer thicknesses on the road surface. It also predicts the snow layer thickness, but I don't know exactly what is the physics behind that, but this is what we know based on some available information. Yes. Then, as the sensor knows what are the water, ice, and snow layer thicknesses, it has an internal model to estimate the road grip value based on those, and also the road surface state class. And as we have collected data, this is the histogram of how the grip corresponds, or what kind of grip values are common, and also considering these different road surface state classes. The dry class is quite common, and there the grip is almost always 0.82. It's difficult to see, but it's this dark bar here on the right. Then, but we know that in wet conditions, the grip varies between 0.6 and 0.8. And in snowy conditions, the grip is out at 0.38 here, this red spike here. And these are the most common conditions that we have collected in our dataset. But the thing is that if we just measure the grip in front of the car here, it kind of like doesn't matter that much, because we want to see far away what is the grip. So therefore, we are using our long-range sensors, which are on top of the car. And in this study, we used LiDAR sensor, Velodyne Alpha Prime, and an RGB camera, and 3 thermal cameras, which are FLIR boson models. And we post-process the sensor data together that we can overlay all these sensor measurements in a single frame, and we chose to use this RGB camera frame as where to project all the data. The first thing which we did is that we projected the road weather sensor recordings in top of the RGB camera image, and we did it in that way that we have recorded the GNSS trajectory of the car. That GNSS system uses RTK corrections, so basically we get the position of the car around the accuracy of 10 centimeters. And then, as we know how the road weather sensor is positioned on the car, and then when we know when it takes measurements, we can kind of like, and we know how the car is going to drive in this road. So basically, because this is post-processing, we can project the future measurement points from the road weather sensor on top of this RGB camera image, because we know how they are located in the image. And that's how we can match these road weather sensor recordings to the RGB camera. Then we have calibrated and synchronized the LiDAR sensor so that we can overlay the LiDAR measurements on top of the RGB camera. On that, we use the reflectance measurements because the LiDAR uses an infrared laser basically with 903 nanometer wavelength. So basically, we can, from that, as the Valeo sensor also uses infrared lasers to measure the road. So we assume that this probably is also useful in our case. And in addition, we had this 3 thermal cameras overlaid on top of this RGB camera as well. It was a bit more complicated procedure, but we first we generated the approximative range image from this LiDAR data, and then we projected the thermal camera pixels to the range image, and then from the range image to the RGB camera. So it was a bit more complicated procedure, but anyway, that's how we got it quite accurately matched to the RGB camera. And we have to also mention that we use the normalized thermal camera values because the thermal camera isn't a calibrated model which would give absolute temperatures on the road. But we thought that this probably might be useful because different types of snow look different on thermal camera. You can see that thick padded snow is here kind of like quite bright, and then sparse snow is more blue, and wet conditions, they reflect the light from the sky, so they might look darker, for example. And then we collected this dataset that we have. The dataset, it's not currently publicly available, but our goal is to publish it at some point. The thing is that the dataset has quite a lot of features, and we want to slightly investigate some of those before making it fully open. But it has basically 37 hours of collected data and 1,500 kilometers recorded with 2 frames per second frequency. So it has over 200,000 frames, and of course it has a variety of different road and weather conditions. And we split in this study, we split the dataset with this geofencing approach. So every 1 kilometer we chose an area and put it to either validation or test set, and had all the rest of the data as training set. We have also 3 separate test drives which we can use as out of distribution tests. Most of the data is collected in the southern Finland. The blue lines here are basically the trajectory of the car during the data collection, but some of the data is also collected in Lapland. And as we have the data, we are training a convolutional neural network to predict the grip from this input data. So the grip prediction model takes the sensor modalities in and predicts a grip map. It actually predicts the grip values for the whole image, but for the visualizations, we just show it for the road area. And then as the ground truth measurements, we use the grip measurements from the optical road weather sensor. And then we know that in these pixels where the grip measurement exists, they should correspond to the predicted grip values in this predicted grip map. And therefore, we can train the grip map that it becomes accurate. You can see that this is a weakly supervised problem because the grip values don't cover the road entirely. It's really difficult to collect grip values for the entire road. To be more accurate, we use the feature pyramid network in this study. So to add more details to this previous picture, we use RGB. We have different encoders for all of these 3 different sensors. We concatenate those features and then make predictions with all of these scales because we don't know at which scale the most important features are, so this is useful. And then the model predicts the grip map, but it also predicts the water, ice, and snow layer thicknesses, and we use that as auxiliary task so that it could benefit. We know that it benefits the model that it learns the grip accurately when we are using this auxiliary task. And as results, we see that the model learned to predict the creep quite well. Here, the yellow values mean that the creep is high, and the blue values mean that the creep is low. And the green values basically correspond to the wet road mostly. You see that the dry road is quite clearly seen, and the wet conditions are seen. And in some of the cases where there are tire tracks on the road, those tire tracks are mostly seen, that they are kind of like they have better grip than the snowy areas outside those tracks. Of course, there are some kind of like difficult scenarios. For example, here there is a pond of water, which is really slippery based on the sensor, and then here it doesn't see that the pond is that deep. So, and here is also some more of these results. We see that the model predicts the creep quite well in snowy conditions and in dry conditions, and also there is some regression in this wet area. But then, of course, in those we don't have that many measurements, for example, here in between, so the model isn't that accurate in those conditions. And when we consider what sensors are the most useful in this study, we noted that the RGB camera and reflectance measurements, they provided the most accuracy when we tested in these validation and test sets. The thermal camera was also somewhat useful, but it didn't provide that much accuracy as the RGB and reflectance camera as these input modalities. But then we don't. If you just predict one creep value, it has problems because you need to also know the uncertainty. If you just know an estimate of the creep value, then you want to make sure that you don't actually slip, that the prediction is not incorrect or something. So basically, we also need to predict the uncertainty of the creep on the road to make sure that the car tires will not start to slip. But this kind of like we want to also address another question, that if that can describe uncertainty be estimated solely based on this road surface layer classification. So basically, do the sensors actually just see that what is the surface type of the road? Is it dry, wet, snowy, or so on? Or do the sensors actually see more that we can do regression on this creep value, so that they can see basically the creep value beyond this surface layer? So we wanted to investigate these two different approaches. Here on top we have this regression approach that you just predict the creep with the uncertainty estimate, and there are many of different methods which do this. Quite common thing is that they have currently those have challenges in out of distribution examples. So we thought that maybe our model might have some, this other approach might have some benefits from that. So basically, when you do this creep predictive uncertainty via road surface state segmentation, you predict the road surface state class probabilities for each of these 5 different road surface state classes. And then, as we know from the training data set, what is the creep distribution for each of these road surface state classes, we can fuse those together to get a pixel-wise creep distribution. So we can predict the uncertainty estimate for each of for all the creep map pixels. And as general, from the results, we noted that if we use those regression approaches, they showed more accuracy. They know better what is the mean of the creep, and also sometimes they could estimate the uncertainty more accurately. But then when we had those out of distribution tests, we noted that this road surface layer classification approach was more robust because it failed less than the other methods when the data was something that the methods had not seen before. So for ROADVIEW purposes, we have used a fused model that we do both regression and this road data state class estimation. So first we predict the mean and standard deviation of the creep to have a normal distribution for each of these input pixels. And then we do this road data state class prediction that we have that the approach that we had before to get a creep distribution, and then we can fuse those distributions together to get this final creep uncertainty distribution. Finally, I would like to show a video. It's on slide and let's see if you can open it. Yes, you can also find this in YouTube. Here in the top image we have the ground truth for the grid values, and in the middle image shown soon we have the mean of the grid prediction, and in the bottom image we have the uncertainty, so the length of the 95% confidence interval of the grid. And basically here the yellow values, they mean that the road is not slippery, and blue values mean that it is slippery. The area is segmented with the previous model from our previous research. It's not that good because it's not trained on this dataset, but works well enough for these visualization purposes. So we can see that the snowy road is seen quite well. When we go to the dry road here, it is seen as dry. The model is uncertain about the edges of the road, which is quite common that if there's different surface type, it's uncertain about the edges. And here we can see that as they are quite narrow tire tracks here, it somehow sees them, but it's still somehow uncertain also on those in these conditions. Then as a last example here, there are wet and slushy conditions, and we can see that as we turn on the left and there's a lot of slush, then the model sees there's more green here, so it sees that there are more slush in those conditions.
Thank you very much, Jyri. That was wonderful. I would kindly ask Julia to share the ROADVIEW YouTube link so that people can see those videos. We have more of those.
Yes, I can do it.
Yeah, that will be great in the chat. Then the next speaker is Petri. Petri, if you can start sharing. And I would kindly also ask you, Petri, to keep it a bit short so that we have a bit more time for the Q&A, because we are already running out of time a bit. Is that fine, Petri?
Yeah, let's see.
Let's see how far, yeah, exactly.
In the end, for example, or something.
All right, thanks a lot. Stage is yours.
Can you see the slides?
We can see your slides, lovely.
Oh, okay, hi. So, hi everyone. My name is Petri Manninen. I'm a senior researcher in FGI, in Finnish Geospatial Research Institute. And today I'm talking to you about HD map positioning of autonomous vehicles. So first, I'd like to give you a little bit introduction and background to the problem, and after that, I will discuss about the requirements for the data, and then I will show how this HD map is built from LiDAR scans and what are the results we have with it. So first of all, about autonomous vehicles, they drive alone there, so they should know their position all the time. In general, 10 centimeter level is considered sufficient. And then also, it's not just about the position, we also want to know the orientation of the vehicles, so which way we are heading. Well, satellite navigation can provide this information. If we combine it with RTK, we can get to that 10 centimeter accuracy. However, if we want to position ourselves robustly, we cannot rely only on one solution. So, because there are actually some problems with the satellite navigation. For example, the signals are not available everywhere, and it's possible that there are false echoes. So, for example, in tunnels, we cannot get any signals, and then if we are, for example, in forest or urban environments where there are tall buildings, so we'll get echoes from those, and then we don't know our location accurately. Then there's GPS jamming and spoofing. Jamming is probably more known, so the small or the weak signals are covered with some very strong signal to so that we cannot get the signals and we don't know our position. Then there's also spoofing, that the that we give false signals to the device, so that that we think that we are in a different position that we actually are, and that's a little bit more difficult to detect. Then also there is this thing that there's no orientation with single measurement from GNSS, so we would need two antennas to have the orientation, but still it's not very accurate necessarily even with two antennas. So alternative solution for positioning is a high definition map. I don't know if you've heard this term before, but basically it can be used for positioning, and it provides both the position and orientation. It's just a pre-built map of the environment where we fit the current view from the sensors, and the positioning accuracy is typically within a few centimeters. And that positioning solution is completely independent of satellite navigation then. There's no unique definition of this HD map, but it could contain the following at least. So the road network topology, which can be used for navigation, could be one layer, and then there's typically the road markings and the road information, for example, information about the road surface and speed limits and this kind of things. And then also information about other road users could be added. And then one layer is these landmarks and features in the map which can be used for positioning. So I'm discussing about this this landmark layer now in here, how to do the positioning. But just to show, so here are some examples about the layers. For example, here in the left, there's road layer, which is the topology and the information how the roads are connected, and then the layer B is the line lanes, which are shown here, and then in this example, these traffic signs are used for localization, for example. Then there's on the right hand side, there's another example of the lane information. How could it be like which lane is connected to which lane, and so on. Then a little bit about the data requirements. So when we drive there with the vehicle, we get the GNSS measurements, and then we measure the LiDAR data. And then if we align the LiDAR data based on the GNSS measurements, as I told that the GNSS is not that accurate, and also the orientation could drift a little bit. So here's one example of that in the left image. We've aligned the data with GNSS, and you can see that it's not so clear than in the right, where we've used scan registration to actually align the data based on how the data looks like. So for example, here if you can see the mouse cursor, so here in the left, the fence is very blurry in this GNSS data, and then when we align the data, it's actually very clear. Also the traffic sign here on the bottom, there's another example, and even the trees are very different. But then there's a problem with the scan registration. So even though locally it looks very nice, but it doesn't know anything about the global position, so the solution drifts. Here's just a trajectory example of comparison with GNSS and scan registration trajectory, and how the drift is, and what are the distances. So it could be several meters or even tens of meters that drift. It depends. So then that position is just not accurate enough. And then in the right hand, there's an example from Kitty dataset that there's 3 different times when we come to the same intersection, and then the building walls, there are like 3 shadows, because each time the GNSS solution is in a little bit different place. So the GNSS doesn't give that like exactly enough either. So we need something else to correct this for building a map. So graph optimization can be used for that. So we have the TNSS, which is globally correct enough. So we use a graph and we use these TNSS positions with covariance as the graph nodes. And then the result of scan registration can be used as the graph edges. And then when we have the uncertainties for this whole graph, all the edges and nodes connected, it can be optimized based on the uncertainties. So basically, if there's a strong link, we know that it's very certain it will not be stretched. And then if there's a weak link that we are more uncertain, we let the graph to stretch more from that point, and that way we can combine both the scan registration and TNSS, and we get the global position, but we get a better fit to the actual data as well, because we are using the scan registration. So basically fusing both of those. Then about the map representation. So since it's recorded with autonomous vehicle sensors, we record actually everything what's in the environment. So also the vehicles and pedestrians, and we don't want them into the map. So the dynamic objects should be filtered out. For example, here in the image, you can see a lot of vehicles in blue color. So they need to be taken out so that they don't mess up with the registration into the map when we are positioning ourselves. Then another thing is that this is a huge amount of data, a lot of point measurements. So we need some compression of the features. It's not feasible to use these maps because they are just too data intense. That for two reasons, because of the limited hard drive, computational resources, and then also the bandwidth of these autonomous or the wireless communication of these autonomous vehicles. So because if we need to transfer these maps all the time through wireless link, it's not feasible. Then one thing to mention is also that the HD map requires to tolerate the changes in the environment. So first of all, we need stable features which don't change too much in different times of year, for example. So tree leaves, for example, drop away and there could be snow. So those tree leaves, for example, they are not reliable enough. And then also we need to keep the map updated. So then the building of HD map. So first I'll just tell you a little bit about what kind of maps there are. So I talked a little bit already about pure point cloud map, that it's not feasible. So it's here. And then, for example, there's something called Octomap. So we just see if we divide the whole space with a voxel grid, and we just see if like certain cube voxel is occupied or not, and then we limit the amount of points a lot, but we don't really know like how these points are actually in each voxel, so we don't have more information. Then there's normal distributions transform, which actually does the same. So we use the voxels, but we compute the normal distribution of the points in each voxel and represent that, and then we can limit the amount of data, but we also know a little bit more how the data is spread in that voxel. So a little bit more about this normal distributions transform, because our method is based on this. So first, if we have the raw point cloud we divide it with 3D voxel grid, and then after dividing it, points in each cell can be represented by their mean and covariance. So just the mean and covariance values are computed for all the points that are in this grid cell. And then the registration can be performed by maximizing the fit to these normal distributions. So if we have a scan, so we just move it so that it'll fit into this model. Then we've developed this method called environment aware NDT, or EANDT, we like to call it. So it forms the map a little bit differently. So it uses semantic information first to understand the scene a little bit, that we use poles and tree trunks, ground, buildings, fences, and traffic signs in this model because we consider that they are quite reliable and don't change too quickly and too much. Then when we have these semantic segments, we separate them into instance clusters. So we separate each individual object in the scene, after which we still divide them into primitives. Here we use planar and cylindrical primitives. And after that, each primitive is divided into cells. So we mostly get these very planar cells in the planar surfaces. And after that, the points in each cell are represented by their mean and covariance similarly to the NDT, and we can use the same registration techniques to register into this map. So if we compare the NDT and EANDT, visually here, we can see that we get a lot neater map representation with EANDT because they're respecting the semantic boundaries and also the boundaries of plane. And this mostly, the EANDT mostly provides flat cells, and it's actually very good for the NDT-based registration because there is very small uncertainty in one dimension, and then we know how the points should lie in that one dimension. With this NDT, there's only one parameter which affects the map, is the cell size, and basically it's a trade-off between data compression and more accurate positioning. So if we have large cells, we have very little information and the map is very compressed. But then if we have very small cells, then we get higher accuracy, but also the map is quite bulky. Then if we compare them a little bit more, we've defined this descriptivity score for the map. So how well the map describes the original point cloud. And we've compared the NDT and EANDT here, and we see that with the same cell size, the EANDT is always has higher descriptivity compared to NDT. If we look at the individual semantic segments, it also applies for its individual segments, so which we are using here. So the building, fence, ground, pole, sign, and trunk, they all have higher descriptivity score with the same cell size. Then if we turn this inversely, so that we have the same descriptivity, so it also means that we get higher descriptivity with the same number of leaves or cells in the map, so with the same amount of information. But it also means that we get the same descriptivity with smaller amount of cells. So we actually have less data, but we have the same description or the map representation. So the EANDT properties are that it has consistently higher map descriptivity compared to NDT. So the positioning accuracy should be therefore higher. And since the compression ratio is 1.5 to 1.75 times higher depending on the cell size, so it means approximately 40% deduction in the size of the map. And then we also have the semantic information, so that could be a useful property in changing conditions, for example. Here's a small case study with Kitty dataset sequence 0. So the data in XY coordinates is a little bit less than 1 kilometer by 1 kilometer, and the trajectory length is approximately 3.1 kilometers. So if we have the original point cloud data of this data, it's almost 10 gigabytes, and if we divide it by kilometer, it's a little bit less than 3 gigabytes per kilometer. If we create a NDT map with 1 meter cell size from the same data, it's around 25 megabytes, and it means approximately 8 megabytes per kilometer. So it's quite a huge drop in the amount of data already. Then if we go to EANDT, it's still 40% drop with the 1 meter cell size, and which results to a little bit less than 15 megabytes, and this means 4.7 megabytes per kilometer in data. So it's still a huge drop from NDT. Now, if we broaden this example to Finnish road network, so we have approximately 450,000 kilometers of roads in whole Finland. So if it would be a raw point cloud, it means more than 1,000 terabytes of data. It's not feasible to use it in any mobile robot or autonomous vehicle. Then if we have NDT map, it's approximately 3.5 terabytes. It's already possible, but too big still. And with EANDT, it's 2 terabytes. It's actually probably still too big map for autonomous vehicle, but we don't need to keep the whole 450,000 kilometers of map in the memory of the vehicle all the time, because if we can drive, for example, 1,000 kilometers a day, so probably having a lot less than this 2 terabytes is enough. And then according to the need, if we go somewhere else, we need to update the maps to that area. Then I have this small video about the building of the map and localizing into the map. So here is our Arvo vehicle, which we are using to collect data here in FGI, and here it is the original point cloud visualized with the intensity values or the reflectance values from the LiDAR. And so first we'll get the semantic segmentation, and now we see that we still have all the vehicles there, and then we filter them out, so we are left only with the reliable things, 10 instance clustering, which I explained, and then we divide it into primitives, and after that into the cells, which will be presented similar to the original entity, so the mean and covariance values. And then the vehicle, when it scans, it measures each individual scan from the environment and fits it into the map and gets the position of the vehicle. So here we are positioning the vehicle into the map and visualizing the scan here on top of the map. So these scan lines here are from the current scan, and then these normal distribution plots are from the HD map.
Thank you very much, Petri. I think that was the last slide, right? Or...
Yes. Yes.
Thank you. We have so many questions. We should maybe quickly go there, visit all this. But meanwhile, I will kindly ask Julia if she can extend the duration of this webinar, because it is fixed to 90 minutes. So we just have like 8 minutes left. I think she can extend that very easily.
Yeah,
So,
I think if we stay in, we can carry on without the event just stopping.
Yeah, very good. Then we start with the questions, and I will visit them one by one because there are so many valuable questions, and they are very relevant questions, I will say. And the first question, maybe you can also read with me. Sergio, it comes to you from Jan-Erik Kalhammer. He is asking, heavy fog, by the way, Sergio is, yes, he is still here. Heavy fog defined as visibility less than 1 kilometer, but fog is defined as visibility less than 1 kilometer. For visibility longer than 1 kilometer, it is referred as haze. For other systems, fog is not really an issue until visibility decreases below about 200 meters. Is the fog results therefore relevant? Even for heavy fog, there should be a big difference between how heavy or how low visibility there were. So, Sergio, are you still here, or are you still facing an issue with the microphone?
Hi, I'm here.
You're here? Lovely. We can hear you now.
Maybe to point me to the question, is it written in the chat? I cannot see it.
If you go to Q&A, maybe I simply share my screen.
Not in the chat. Okay.
I simply share my screen. No, here. And this is the last question, and I will make it a bit bigger. It's about the fog visibility in foggy conditions. So that's the question. Did you get it? Or
yes, okay.
If Jan is here, we can also ask him for more elaboration on the question.
In our system, the fog is not really an issue if visibility decreases until visibility decreases below 200 meters. Actually, yes, this might be per definition, but the customers requiring up to 300 meters range for normal obstacle tracking. So it is more than this 200 meters. That's why it is relevant in some scenarios.
Okay, so it's basically more use case relevant.
Yeah.
All right, thank you. Then the next question is also to you. According to which sensor setup could help to unlock upcoming regulations such as this one? Can we rely on AI-based models for AEB scenarios since there is a lack of training data for the same?
This is a $1 million question, so I cannot.
Yeah.
So this is only a guess that if we can rely on AI-based models. So as I said at the end of my presentation, from my opinion is we need to use hybrid models. So a combination of classical methods together with AI to cover mainly the long tail scenarios, as you also mentioned, that the ODDs are fully covered, and also those which don't have enough training data.
Thank you. Next question is also again to you. Spray was categorized as rain, snow accumulated over 1 hour. However, normal roads are tapered, slope convex. There is elevation change because of that. Why the accumulation over 1 hour may not be very meaningful. The amount of water spray is more a function of the instantaneous level of water on the road. For snow, it's very dependent on the type of snow. Some snow create a whiteout, while other types may not, may be more an issue of accumulation on the sensor surface. With this uncertainty in what the instantaneous level of water or snow characteristics, how to compare the results?
Yeah, this is a very valid question. It's fully true. And we need to define together with the customer scenarios in which those levels are tested again. So if we define the main ODD is going to be highway, then which type of highway? So in Europe, it's different than USA, also the asphalt sometimes. So it's not only the level of precipitation or the level of environmental effect, is also the type and also the road conditions. Regarding the accumulation on the cover, in the end, we need to be able to detect that level of blockage on the sensor, independent of the type of artifact which is accumulated. So regarding that dirtiness on the cover, we shall be able to cope with all different kind of snow, and of course not only snow, but dirt and other artifacts.
But
So,
do you have any mechanical cleaning of the sensor, automatic
so
cleaning?
Valeo provides the option to have a cleaning, so to trigger the signal for a cleaning system. But in any case, this shall be triggered based on some flag, so that we need to provide that activation flag.
Thank you. One more question to you. Nice talk. When the vehicle is on the road, how do you estimate or measure what the rain and fog values are at any given time?
We cannot. That's definitely. We cannot. That's why we need to define the requirements. Those are the KPIs achievable in this level of rain, this level of snow. And those are defined and tested on deterministic scenarios, deterministic tests. Now what
So
happens
it's for
on the road is,
it's only for the KPI measurement.
Yeah.
How dependent are your detection and classification algorithms on accurate knowledge of the impact categories?
Indirectly by the KPIs. So we don't need to know there is a 0.5% millimeters per hour of rain to adjust our tracking, but we might be impacted accordingly.
Okay, the next question is to Jyri, but meanwhile I will again ping Julia. It looks like we have only like last minute, so please make sure that we will not lose the connection. I hope not. Okay, question to you, Jyri. Would it also be possible to detect potholes and road defects or even road bank failures in time? I'm thinking of an erosion damage caused by torrential rain or temperature changes and the ability of the driver or vehicle to react in time.
Thanks for the question. This is not especially my field, so it's also difficult to answer because it also depends on the resolution of the sensors in general. One thing which I want to mention is that I've heard, or at least if I understood correctly, the thermal cameras might actually see the road cracks on the road surprisingly well. So and maybe also potholes. So that's
but
also.
When it comes to this grip estimator sensor, Vaisala sensor in the front, is it any useful when it comes to there is like a hole or anything on the road surface? Is it?
I assume not. I assume it mostly assumes that most of the road is asphalt, and when it's something else, then it probably considers it that the accuracy is less, that it's out of distribution somehow.
So the sensor, the Vaisala sensor, is somehow useless when it comes to these cases. I assume you answered the question. Then the next question, regarding FGI presentation on road grip, I think it comes to you. The thermal cameras, did you use the raw data or data that dynamically was adapted to the current range of temperature, actually received radiation? Normally, the camera's normal output mode adapts to the dynamic range in the current scene. If so, how did the machine learning algorithm handle this uncontrolled variation in input data?
Yes, we recorded the raw data, but we normalized each thermal image to kind of like so that the mean is 0 and the variance is 1. So basically, we lost in that way. We lost the because the raw data included the thermal flux from the road, but it varies because the camera does the calibration all the time when driving on the road. So it doesn't correspond exactly to the actual temperature. But then I need to also mention that we couldn't use the actual temperatures of the road because the models that we use would learn to overfit to those specific temperatures, because then we would need to collect data on all different temperatures of the road, because if we basically the data was collected in around 20 days. So if on one day the temperature was -5 degrees, and then the models would learn that, okay, it's the day of -5 degrees, so the grip is like this. So that's why we didn't use the absolute temperatures.
Thank you. And then a question from you too, Sergio.
Yes.
What was the LiDAR sensor model which recorded the dense point clouds? Is it from Valeo? Which sensor was it, Sergio?
Yeah, it is. This is Valeo. It's our Scala 3 sensor. Is yeah.
The solid state.
Current.
Is the solid state one or is the rotating?
It's a rotating mirror.
Okay. Lovely. I think, yeah, I'm done with all those questions, but I have also some questions to speakers, if you don't mind. The first question is to Sergio. Sergio, I actually like your presentation very much, and it matches very much with what we are doing here in my group. And one issue we observed in the project ROADVIEW is that whatever you develop AI or classical geometry-based approaches, when you switch to another, the same sensor but with higher resolution or lower resolution, things are not working at the same quality. So how much how relevant is the resolution when it comes to the perception? So you show these nice dense point clouds, and you show that it filters out. I agree, it works fine. But what if I switch to a point cloud which are a bit sparser? From 128 to 64, for instance, do you observe the same performance, or there's a huge performance drop, or what's the difference?
So actually, the journey we are doing it the other way. So we are going from low resolution to higher resolution. And yes, the performance is different. So the algorithm needs adaptation in any case. On the other hand, we are trying now AI-based applications on the dense point cloud. Although we come from a sparse point cloud in the previous generation where only geometrical models were used. So yeah, it needs adaptation due to the point cloud density, but also due to the methods used.
Thank you. Maybe I can also ask one question to Petri. Petri, I think the core contribution of your work is semantics-aware mapping. Can we phrase it that way? Like, because your ultimate aim is to reduce the amount of data by using the contextual information to create your map.
Yeah.
And how is this in the literature? I mean, are you the only one doing that, or is it like because semantics is crucial information. We use it all in the perception pipeline heavily, and it helps a lot. And now your information is more top-down, so you know the environment, then you classify all this, and then down-sample the information. So how different is yours than the state of the art? Or
sorry, what do you mean? How different is mine?
You're from the state of the art, so from the literature work. So is it you are the only one using the semantics information when it comes to this?
Well, currently I haven't seen that no one would be doing it this way, that they would like to do a map into which to position the vehicle afterwards. Typically, it's just SLAM solution, so it's LiDAR autometry and then some SLAM solution, but it's not all together because this it's really difficult to align the data that way that you can actually create a map, because there are various things. There are calibrations and stuff which affect the map quality. So you could maybe have a nicely looking map, but it might not correspond to the global coordinates if you don't combine all the information.
Let me go one step further. I mean, you have a level where you have those Gaussian blobs to help the localization. Is there any way to go one more level down to make it even sparse?
Yeah, I want to try that, but I haven't tried that yet. Yeah.
Well, in which direction now? How can you do that? Just throw some ideas. I'm a bit curious.
Yeah, just to, for example, now there are cells. So if we use larger cells, because they are anyway in planar places, for example, planes. So then does it matter if I have 1 meter cell size or 4 meter cell size, because then the uncertainty still is small in one dimension. So,
Thank you.
It should be good.
Thank you. Maybe the last question goes to Jyri. From your slides, I understood that thermal cameras are useless when it comes to this application. And I actually heard similar comments from other experts in the field, like people were using thermal cameras in bad weather conditions. So is it also the same with you? So do you have the same impression, or is there any case where thermal cameras are really useful?
Yeah, well, the experience, how to say, my experience is that when you consider semantic information, kind of like in general, that you can see that I think thermal camera kind of like separates different surface types and objects quite well. So it will, in that case, it would be quite useful. Also, that it sees during night conditions, so that is probably quite useful.
Good. With that, I again thank all the speakers. It was wonderful. I like the presentations very much. And again, I remind that we are recording this webinar, so we will also release the videos on our webpage, so you can reach them afterwards. Again, thanks a lot. Special thanks to go to Mario, who you see now cannot join, but Julia, she's helping us a lot for the admin-related issues. Thanks a lot, Julia. And last but not least, I also thank all the participants. Thank you very much for those nice questions. We see each other hopefully in the next webinar. Thank you.